In the conceptual videos, we learned about potential energy and kinetic energy. Potential energy is the energy that something has due to where it's at. Now, in the case of gravitational potential energy, which you'll sometimes see as GPE, it's equal to the weight of the object times the height of the object. Now, we are always referring to the height of an object. Let's say I have an object up here in the air. We have to talk about what it's relative to. So if we use the ground, we would say that the height equals 0 on the ground, and the height is something else up here. But let's say I had an object and I wanted to lift it not from the ground, but off a table. So I have a table, something like this, and I take an object and I lift it up. In this case, since I'm lifting it from the top of the table, I would say that the height of the tabletop is 0. I can call any height I want to 0. Most of the time, we're changing the potential energy of something. So the change in that potential energy is due to the change in that height. So if I lift something up, I'm changing its potential energy. If I lift it up against gravity, I'm giving it energy. If I lower it down, I'm taking its energy away. Kinetic energy is the energy that something has when it's moving. To calculate kinetic energy, you multiply 1/2 times the mass times velocity squared. And you might notice that kinetic energy depends on the same two variables as momentum. Momentum is just mass times velocity. Kinetic energy is a different configuration of those two variables. And it's a different idea, but they're very, very related. And as a matter of fact, if you have no velocity, you don't have kinetic energy, but you also don't have momentum. If you are moving, you have both momentum and kinetic energy. One of the things to point out about kinetic energy that's different is that it relies on the square of the velocity. So if I increase the velocity, I make the kinetic energy go up exponentially. In other words, if I double the velocity, 2 times the velocity yields 4 times the energy. 3 times the velocity would be 9 times. 4 times the velocity, 16 times, and so forth. So velocity affects the amount of kinetic energy a lot more than mass does. In momentum, they have an equal amount of impact on how much momentum you have. But in kinetic energy, velocity is more important. If I have a situation with no friction, where I have a height change and a speed change, in those circumstances, we would say that energy is conserved. On your worksheet, I have this big formula that looks pretty scary, but is actually very useful and not so scary once you get what all the little symbols mean. This is a statement of what we call the conservation of energy. The mechanical energy, the 2 types of energy we learned right now, which are potential energy due to gravity and kinetic energy, are represented in this equation. Now, the little zeros mean before, and the little f's mean after. So what I'm basically saying here is that the total energy before equals the total energy after. And the question is, before and after what? Well, typically it's before and after a height change. So for instance, we're going to do several practice problems, but quite a few of them look something like this. Let's say I have a pendulum, and I raise it up, and I have it sitting still, so it has no kinetic energy. Remember, things have to be moving in order to have kinetic energy. But because I've raised it up above the place where it's going to wind up when I let go, it's up some height above the lowest point, which that's the lowest point is what I'm going to call h equals 0. Since it's up there, the potential energy before I let go is mgh. Now I'm going to let this thing go, and it's going to move down and be moving at the bottom. Now, since I define the bottom as the place where the potential energy is 0, at the bottom it has no potential energy. But it is moving, so it has kinetic energy. And since there's no friction, all the potential energy I had at the top equals all the kinetic energy I have at the bottom. Now, if I go back up to my equation, what that looks like is at the top, I have no kinetic energy, so this term goes away. And at the bottom I have no potential energy, so this term goes away. And what I wind up with is what's left. The mass times g times the height that I started with equals the 1/2 mv final squared that I end up with. All the potential has turned into kinetic energy. Now when you go to do the math of this, I'll do an example. Let's say we dropped it from 5 meters up. We raised this thing all the way up 5 meters vertically, and we want to know how fast it's going to go at the bottom. Well, one of the things I can see is that mass is on both sides, and it's going to cancel. And if I plug numbers in, g is 9.8 meters per second squared. The height I just said was 5 meters, and that equals 1/2 v final squared. To solve this, I'm going to multiply both sides by 2. And since the right side is v final squared, I'm going to have to take the square root of both sides in order to get my answer. And if I were to do that in this case, I get that the v final is 9.9 meters per second. You notice I did not need to know the mass of my pendulum in order to do this because it doesn't matter. All the examples that we're going to focus on in this class are cases where we're going to go from all potential to all kinetic or all kinetic to all potential.